Okay, so I'm Guillaume and we are group 4, and Ms. Jordi and Gerard. We are going to explain you the exercise 5.17. We've divided the problem into several parts. The first one is introduction and plan, so let's start. Here we have the exercise and it says the following. A rectangular loop of wire has sides A and B, so we have to compute the magnetic field at center C when it carries a current I. Here we have the figure, and very quickly some theory keys we have to consider and we'll use during the execution part are these ones. We're handling with electric current as a source of magnetic field, so we'll treat it like that. The right-hand rule that we have seen it so many times, and particularly we'll work with the particular case of a field of a straight wire. Here we have this scheme we have prepared to make more clearly the plan, which is divided by two parts: the computation of the field, that is beta, and before compute it. The first issue we have to consider before compute beta will be the symmetry. Why to consider the symmetry? Because the figure is a rectangle and the point C is located in the middle of both sides, I mean in the center of the figure. So in a certain way, we have to take advantage of it. So we conclude that the modulus of the field created by the sides of equal length will be the same. I mean, A1 and A2 in modulus will be the same, and B1 and B2 in modulus will be the same. The second step, the direction. Here we use the right-hand rule to know where the direction of beta goes, and as all the field go to the same direction, that is minus k, they add each other up to make the total field. And we conclude this equation by substituting and considering the direction of all vectors. Okay, then as we know the direction of beta, that is minus k, we'll just compute the modulus of the field and later we'll assign the direction minus k. Now let's just start with the next part, that is the computation of beta. Since we handle with a magnetic field produced by a circuit, we'll use the Biot-Savart law. Like I said, as we only have to compute the modulus part, we'll develop the formula and start from here. The next step in order to compute beta will be perform some substitutions relating the vector and the angles as we can see in these examples, so that we'll be able to compute the integral. Then at last we solve the integral. We have and we'll obtain these two values, and to finish we have all we need. We sum the two modulus multiplied by the two wires of each side we have and assign the direction minus k. So that's all the plan, and for the next part, the execution part, we'll assume we have computed before the direction of the resulting field, that is minus k. Initialize with it and focus only to compute beta through this equation.
Okay, so now going through the resolution, we're going to develop Bio-Savart law. That basically tells us that we can calculate the magnetic field created by a small size of wire at a point P, which is at a distance R. And beginning with this equation, we can switch to the second equation that is working with modulus. If we perform a change of variables and we apply the Pythagorean theorem, r squared is equal to z squared plus d squared, we obtain the third equation. And d of L is equal to d of z because it follows the z-axis, the wire, right? So we can also perform a change of variables. Now in this case, working with another angle of this triangle that is shown in the slides using z is equal to d times tangent of theta, and then making the derivative. We can also use this trigonometric equation, 1 plus tangent square of theta is equal to 1 over cosine square of theta, which is quite useful in this case. And we will end up having this equation. Now, if we evaluate that theta 2 and theta 1, we will obtain this formula, which is in general. Okay, so now focusing on the exercise, we're gonna denote x as a over 2 and y as b over 2. And we're gonna now focus on sinus of theta 2 and theta 1. Now, using this relation we obtain the result, and the sinus of theta 1 will be equal to sinus of theta 2, but with reverse sign. That is because I choose the reference frame as the following. Every angle that opens up above x is positive, and on the contrary, it's negative. Okay, so if we apply Biot-Savart's law, we'll obtain the result, but we must remember to double it because we want the magnetic field created by both of the wires. Now we're gonna do the same, but with wires of length A. The same change of variables. Sinus is easily computed. Remember the negative sign in one angle. And then computing for one wire, we obtain the result, and for both wires, we have to double it, right? And in the end, we have to add all the results simply, and taking common factor, we obtain the final result.
Now we will proceed to the next section, discussion and analysis. First of all, we are going to start discussing the units of the result. Here you can see our result, and it has to be expressed in Teslas, the International System unit. However, 1 Tesla is equivalent to 1 kilogram divided into ampere to the second to the square. From here will come our deduction. Now we start looking at the result. We found that vacuum permeability, which is expressed in relation of force and intensity. The force in the International System is expressed in newtons, but here we have put the equivalence with kilogram meters divided into seconds to the square. Intensity is measured in amperes, so if we put all these equivalents in the vacuum permeability, gives to us this expression. Finally, the length of the sides A and B are measured in meters. Now we are going to substitute all the equivalents in the final result. As you can see, both meters and amperes can be crossed as they are in the numerator and denominator. After crossing them comes out the result that we were looking for, kilograms divided into amperes to the second to the square. That is the equivalence with Teslas, so we know that our result may be correct. The second analysis is compare our exercise with an infinite wire and see what are the differences. Both start from the Bio-Savart law. We only want to know the modulus, and the formula simplifies in this way. Differential of L transform of differential of x multiplied by the sinus of the angle divided into b to the square, where we can extract by trigonometric equalities that sinus of theta is equal to r, and b is equal to the square root of r to the square and x to the square. And computing the integral, we arrive to the general solution of the infinite wire. Here is the general formula of one finite wire that Jordi has explained where it comes from. Where are the two main differences? The first one is respect d and b. While d is constant and can go out of the integral, b depends on x and r, and you have to use trigonometric equations to solve the integral. And the second one, which I think that is more obvious, are the limits of integration. Infinite wire goes from minus infinity to infinity, while the finite wire is computed between the two angles that depend on your reference frame. Finally, we thought that we could compare our example to one very similar in electrostatics. Look at this first image and think about what would be the electric field at point P if lambda is constant. I give you 10 seconds to think about it. I think you all may have come with the correct answer. By symmetry, we can easily watch that the electric field at point P is 0. Also, you could have done by developing the electric field formula by all the fragments of the wire, but the answer will be the same. Now, let's focus in our exercise. As Jordi and Guillem have said, our final result is the sum of the 4 fragments of the wire. Why? Please pay attention to the Bio-Savart formula and compare it with the electric field with respect to the obvious difference. The main one is the cross product, where you can do it for all the sections of the wire and you will see that all the results go to the same way, inside the screen. Also, you could do it by the right-hand rule. For example, the below section would be like this. Intensity goes to the left. The vector goes up, so the magnetic field goes inside the screen. And the same for the other 3 sections. So, now we have finished our presentation, and if you have any doubts, you can proceed. Thank you very much.